Hi guys, I'm Prof Joe and this is part of my lecture on measurement technology. Today with part 2 of the chapter Oscilloscopes, dealing with adaption units, adaption resistors and probes. Okay, last time we learned something about voltage sources for oscilloscopes, and now let's assume we have one of those sources, as we know, which might be connected directly in DC mode or indirectly via a capacitor in AC mode to our adaption unit. And that unit would be connected to the analog digital converter and so on. We won't talk about that stuff, we'll focus on that stuff over here. Okay, what is that adaption unit about? It's about stepping down, getting down, for example, input voltages which are too high. Meaning when there's an input of some kind of 100 volts, we only can convert up to 1 volt. We have to do a step down. We have to divide that voltage into a voltage which can be consumed by our analog digital converter. At the same time, perhaps here's some more amplification unit to even get to display smaller voltages. But now let's assume our goal is to step down the input voltage because we don't want harm our analog digital converter. Too low voltages are no problem, too high voltages are a problem. So what we could do is what we do in any which measurement device out there. We do some splitting of our voltage with a voltage divider. This time being complex, meaning if that's our voltage, let's call it U1, a complex voltage, which is applied over here to the oscilloscope, we get something like that for our unit. Two resistors over here, R1 and R2, and two capacitors over here, C1 and C2. Now what is given to the oscilloscope is only part of the voltage, which is U2 and which is just taken from the part C2 of our voltage divider. Now that voltage divider is complex, so we have two complex resistors in here, that one and that one. That is, let's call it, for example, Z1 or 2. That's Z1, that's Z2, and that is the parallel connection of a resistor and a capacitance, meaning that is R1 in parallel to C1, the resistance of C1, and that is 1 over J omega C1. That's the complex resistance of C1. Calculating that stuff gives us R1 or 2 over 1 plus J omega R1 or 2 C1 or 2. Awesome, because now we know everything. That's a normal voltage divider, and we take the voltage applied or supplied by U2. So what we are interested in is the ratio of U1 to U2, the complex ratio. Those are complex voltages because we deal with alternating currents and voltages. Now, that's quite clear. That's a normal voltage divider. So we have Z1 plus Z2. That's the voltage equaling corresponding to U1. And we have Z2. That's the voltage corresponding, the voltage taken from our complex resistor Z2. We can calculate that stuff. Basically, that's 1 plus Z1 over Z2. And now that can be further calculated and evaluated to be 1 plus R1 over R2. That's the thing we would expect when there's only the ohmic resistor over here. But now the complex stuff comes into play and we get 1 plus J omega R1, no, it's R2 C2 in the denominator and J omega R1 C2 C1 in the denominator. Okay, looks harmful somehow, is not harmful at all. What do we want? That's the first question to ask. We want a ratio which does not depend on the frequency, with no dependence on the frequency, omega. Now that makes it clear. That part is all right. That part gives us some problems. So what to do? Simple way of solving the problem, we say that part has to be 1. And that means, looking at numerator and denominator, J omega R2 C2 has to equal J omega R1 C1. Then numerator and denominator are the same. That means R1 C1 has to equal R2 C2. The product of both ohmic resistance and capacitance has to be equal for both complex resistances over here. Still, we can define our ratio because, for example, we can choose R1 and R2 beforehand. Meaning, if we want to split the voltage in a ratio of 10, we choose R1 to be 9 times larger than R2. Okay, R1 and R2 are fixed now, for example, with 1 mega ohm and 9 mega ohm. And now we can choose C1 and C2 arbitrary to fit our needs. Normally C2 and R2 are given by the oscilloscope itself, so that's the internal resistance of the analog digital converter and the capacitance of the whole setup, the whole electrical circuits in the oscilloscope. So we are free to choose R1 and C1 in a way that R1 guarantees us that we get the ratio we want to have, and C1 guarantees us we get a frequency independent way of measuring the voltage coming in. Why is it so important that this is frequency independent? Simple said, imagine it would not be frequency independent. Imagine, depending on the frequency, the ratio would change. So the signal displayed would change depending on the frequency. Or in other words, the amplitude of your cosine or sine would change depending on the frequency. To make it very concrete, imagine you have a sine with 1 volt amplitude. And for 10 Hertz, you can see 1 volt. But for 1 megahertz, the same amplitude would be displayed, for example, as half a volt or even less. That is something which is not quite usable. You could do an awesome load of calculations, but on the other hand, you could just choose your capacitances the right way and you get rid of that behavior. That is something which can't be corrected digitally very easy and very correct, but which can be corrected very easy in the analog way within an analog circuit. That's why this is still used for even digital oscilloscopes. Okay, having said so, we get into another range of problems dealing with the connection of signals over here. When we have alternating voltages and currents, those always are something like antenna signals, meaning when you have a single wire, you hold it in the air and you apply a sine voltage to it, that will exert a radio signal. It's like an antenna. So what happens when you hold up another wire next to it, you know how radio works, that antenna will receive the signal from the sender over here. So some signal will be recorded over here too. And now imagine we do the same stuff using our oscilloscope. For example, placing your power plug next to your measuring wire. What will happen? Your power plug will have some radio signals with around 50 Hertz, which will be received by your wire connected to your oscilloscope carrying your measurement signal. That's bad. So you get a mixture of a 50 Hertz signal and your measuring signal. That's something you don't want. That's the reason why, for getting rid of those signals from outside of your measuring wire, you normally use a coaxial cable to connect to your oscilloscope. What is such a cable? It's nothing more than the ground at the outside, building something like a cage around the measuring line, which is not the ground, which is in the center. And that gets you to the fact that any signal coming along here will be directly fed into the ground and will not disturb your signal in the mid of the wire, in the center of your wire. So having such a coaxial cable is awesome because you get rid of those disturbances, those radio signals from the outside when there are heavy radio signals in the outside, or when you have very small measurement signals which heavily display those disturbances, those disturbance signals, those disturbant radio signals from the outside. Now, along with those cables comes another problem. Those cables have capacitances. For sure, that's nothing more than a capacitor over here. So they have real measurable capacitances. And now remembering that stuff, we get a problem because that whole setup here has a capacitance itself. Let's call it CE. That's the capacitance of our oscilloscope itself. The input capacitance. And now, knowing that stuff, we get a problem because by connecting a cable over here with its own capacitance, we change that capacitance, at least change C1, the C1 capacitance, and by that, again, get somewhat frequency dependent. That's not what we want. So let's sketch what we see. So, coming from our U2 signal we are taking over here, that is somewhat taken from a internal capacitance CE and the internal resistance RE of the oscilloscope itself. Imagine all of that adaption unit and all of the oscilloscope combine into those two parts, the ohmic resistance and the capacitance of our oscilloscope. Now those are connected on the other side to our U1 over here. And now that stuff, we get the cable over here, which holds its own capacitance. Let's paint it like that. CK. And now you see the problem. That capacitance gets changed by that one. They get added, and by that your frequency independence we discussed beforehand gets destroyed. So what is the trick? We use a probe. Again, we use a special unit which holds its own resistance RT and adjustable capacitance CT like that, and which now is connected to your desirable signal U1, let's call it E or P, so it's clear it's the signal we record by the probe. Now what can we do now? We can adjust that capacitance to keep us frequency independent. And we know everything we need to know about that, because now we can write down, okay, we know that's, looking at that stuff, we get one complex resistor over here, one complex resistor over here being connected in parallel. Just repaint that picture in another way and we'll see those two units are in parallel connected resistors. That's the same thing as over here. But we have different capacitances and resistances, meaning for frequency independence, that condition R1 times C1 equals R2 times C2 has to be fulfilled by that concept also. So we have that one complex resistor over here, which is CT times RT, and that has to equal the stuff over here, and this gets adapted CK plus CE in capacitance by adding the cable capacitance. And now you can just adjust CT to fulfill that equation and to get frequency independent. Again, the way how to work with that stuff is the same. RT most of the time is choosable also. And for example, there's some ratio of our incoming voltage at the probe to our incoming voltage at the oscilloscope, which you can adapt using the input resistance of your oscilloscope and the input resistance of your probe. So choosing the probe resistance will give you some ratio over here. Often that's a ratio like 10:1 to get down the voltage for the oscilloscope. Having done so, the next step is to adjust CT so that this equation gets fulfilled. Now the question is, how to adapt that? Yes, you can calculate along, but doing the practical stuff, you won't be able to do a lot of adaptions or something like that. So what you normally do is to adjust your probe, to adjust the complex resistance of your probe, to adjust the capacitance of your probe, is you apply a known rectangular voltage signal to your input of your probe. You know that signal. And now you watch what is displayed. And let's paint it this way. What is displayed? And now what you want is exactly the same signal, for sure. That's our wish. But when CT is not adjusted correctly, you will see some deloading or loading curves, which denote that the high frequencies coming along with the sharp edges, the rectangular signal, produce some frequency dependent behavior of the amplitude in your signal, and that is what you see over here. Speaking about electrical circuits, those are loading and deloading curves of the remaining capacitance in the system, of the remaining capacitance which can be loaded or deloaded. By doing such a compensation with a probe and getting the ideal signal, you produce a system which has capacitances altogether spread all over your electrical circuit in the system, but which capacitance overall together is zero, which loadable and deloadable capacitance overall is zero. Okay, that's important stuff about connection and using oscilloscopes. And those are the most important calculations, including those, because that's the stuff you have to deal with when doing real measurements. You cannot just neglect that your system has capacitances, and those capacitances give you a frequency dependence. You cannot neglect that fact. So we have to deal with that. Ideally by knowing about your resistances, about your ratios, and about your capacitances. And at the same time doing the adaption via a real measurement, via a probe signal, which gives you an insight into the frequency dependence of your signal itself. When doing so, you can be sure to record the right signal and to record the right stuff using an oscilloscope to be dealt with by an analog digital converter, which we will talk about in the next chapter. Hopefully you enjoyed it. See you next time.